Almost every material we desire is hidden somewhere on the planet, right beneath our feet. From gold, highly valued in jewelry, petroleum, which fuels our cars, the Earth offers us an impressive deposit of resources capable of meeting virtually all our needs. In total, there are about 90 known natural elements, and most of them are metals. Despite being incredibly useful, metals are not always ideal for certain applications. Iron, for example, is extremely strong, but it has some limitations. It can be brittle, and also has the problem of rusting easily when exposed to damp air. Or perhaps we can talk about aluminum. It is extremely lightweight, but in its pure form, it is too soft and weak to be used in some products. That's why most of the metals we use in everyday life are not actually pure metals, but alloys. Alloys are combinations of metals with other substances made to make them stronger, more durable, lighter, or enhanced in some other way. Although you may find an alloy described as a mixture of metals, some alloys actually involve only one metal combined with non-metallic substances. A good example of this is cast iron, which is an alloy composed of iron mixed with carbon, a non-metal. The best way to understand the concept of an alloy is to think of it as a material made from at least two different chemical elements, one of which is always a metal. The predominant metal in an alloy, which usually represents more than 90% of the material, is called the base metal or parent metal. These combinations of metals with other chemical elements form the basis of many materials we use in our daily lives. The process of creating metal alloys is one of the most effective ways to adjust the properties of a metal to meet specific needs. This makes the use of materials much more versatile, as alloys can be designed to withstand extreme conditions, such as high temperatures, corrosion, or even heavy impacts. For example, stainless steel, which is widely used in kitchen utensils, automobiles, and construction, is an alloy of iron, chromium, and sometimes nickel. Chromium is added to increase corrosion resistance, making the material ideal for humid and acidic environments, such as in the food industry or medical equipment. Another famous example is bronze, an alloy composed of copper and tin, widely used in coins, sculptures, and machinery parts. Bronze is known for its hardness and resistance to wear, being stronger and more durable than pure copper. Additionally, copper itself is used in alloys like brass, which combines copper with zinc, creating a material that is more rigid and resistant. For example, cast iron is an alloy composed of iron, a metal, mixed with carbon, a non-metal. The best way to understand an alloy is as a material made up of at least two different chemical elements, one of which is a metal. The primary metallic component of an alloy, which usually represents more than 90% of the material, is called the base metal or parent metal. The other components of the alloy, known as alloying agents, can be metals or nonmetals, and are usually present in much smaller quantities, sometimes representing less than 1% of the total. While some alloys may be compounds, most of them are solid solutions. If you observe a metal with a powerful electron microscope, you will see that the atoms are organized in a regular structure called a crystal lattice. Imagine a small box full of marbles. When observing the structure of a metallic alloy, you would see something quite similar, where in addition to the atoms of the base metal, there are also atoms of the alloying agents spread throughout the structure. When the atoms of the alloying agent replace the atoms of the base metal, we have what is called a substitution alloy. A substitution alloy only forms when the atoms of the base metal and the alloying agent are of similar size, and when these elements are close to each other in the periodic table. Brass, for example, is a substitution alloy based on copper, where zinc atoms replace between 10% and 35% of the copper atoms. Brass works as an alloy precisely because copper and zinc are close to each other in the periodic table, and their atoms have similar sizes. However, alloys can also form when the alloying agent or agents have atoms much smaller than those of the base metal, creating a different but equally functional structure. When the atoms of the alloying agents are much smaller than those of the base metal, what occurs is a formation called an interstitial alloy. In these cases, the smaller atoms fill the empty spaces in the crystal lattice of the base metal. This can alter the material's properties, such as hardness and wear resistance. An example of this is steel, which may contain carbon atoms much smaller than those of iron. The carbon occupies the empty spaces in the iron's crystal lattice, making the steel stronger and more resistant. This type of modification in the metal structure can have significant effects on the alloy's mechanical properties. When the crystal lattice is altered by these smaller atoms, the movement of the base metal atoms is hindered, which increases the hardness and resistance of the material, but can also make it less malleable. Therefore, the process of creating metallic alloys, whether by substitution or interstitial insertion, offers a wide range of possibilities for developing materials with desired characteristics, adapting them for different applications, such as in construction, electronics, automobiles, and many other sectors. In this type of alloy, the atoms of the alloying agent fit into the gaps between the atoms of the base metal, forming what is known as an interstitial alloy. Steel is a classic example of an interstitial alloy, where carbon atoms, in a relatively small amount, occupy the gaps between the large atoms in the crystal lattice of iron. But why do we need these alloys? Alloys are created and used because metals in their pure form do not always have the ideal properties for certain tasks. Iron, for example, is excellent as a construction material due to its strength, but when combined with other elements such as chromium, it forms steel, which is stronger, harder, and resistant to rust. Another example is aluminum, which is a very light metal but very soft in its pure form. If we add small amounts of other metals, such as magnesium, manganese, and copper, we obtain an aluminum alloy called duralumin. This alloy is strong enough to be used in the construction of airplanes, offering an ideal combination of lightness and strength. These examples show how the creation of metallic alloys is essential to meet the specific needs of different industries and applications. When a metal is mixed with other elements, whether to increase strength, improve durability, or create characteristics such as lightness and flexibility, the resulting alloy is much more suitable for a particular use than pure metal would be. Furthermore, metallic alloys can be designed to withstand extreme conditions. For example, in industries like aerospace or automotive, where lightweight material with high strength is required, the use of aluminum, titanium, and other combinations of alloys makes it possible to create products that would not be feasible with pure metals. Titanium, for example, is widely used in aircraft parts due to its lightness, corrosion resistance, and high mechanical strength. In sectors such as construction and tool manufacturing, steel alloys with elements like nickel or molybdenum provide wear resistance while maintaining the necessary durability to withstand large stresses and pressures. The combination of metals with other non-metallic elements can also produce alloys with resistance to very high temperatures, such as those used in airplane engines and turbines. In addition to fusion, there are other methods to create alloys, such as metal spraying or rapid solidification, which are used to create materials with specific characteristics. These methods allow for more precise control over the composition and structure of the alloys, which is especially important when aiming to enhance certain properties, such as corrosion resistance or the ability to withstand extreme temperatures. This control over the formation of alloys and their properties is one of the most fascinating aspects of materials engineering, enabling the creation of innovative and highly effective solutions for various applications in industries such as automotive, aerospace, electronics, and even construction.